Welcome, hello everyone. My name is Sofia Trentafilidu and I'm one of the vice presidents on the IS&T board of directors. I want to welcome you to the second IS&T's new seminar series featuring the best student research from electronic imaging 2020. Over the next few months, we will be showcasing research by students that led to Best Paper and Best Student Paper awards received earlier this year. I want to take a moment to thank an individual donor who wishes to remain anonymous, as well as the Imaging Science Group of the Royal Photographic Society for supporting this program. Their support will help us provide electronic imaging registration grants for students and ensure the continuation of this online seminar series. Before we begin, I would like to take a couple of minutes to tell you about IS&T and in particular the Electronic Imaging Symposium. Oops. For those not familiar with the Society of Imaging Science and Technology, the society is unique in that it brings together nearly an equal number of international researchers and practitioners from industry and academia. This makes it a great place for students to showcase their work to prospective employers and for those in industry to learn about exciting developments in imaging research. IS&T spans imaging across applications from capture through processing to output to vision. Our conferences, courses, and journals offer a place to share their latest innovations with networks of others who have a love for and curiosity about the world of imaging. IS&T's breadth is best found at the Electronic Imaging Symposium, where 20 conferences and more than 25 courses offer everything from AR, VR, and autonomous vehicles to big data, remote imaging, and mobile devices. Two great features about electronic imaging are the open access proceedings and the ability to submit a journal paper, which of course gives you a journal citation in lieu of a proceedings paper, and still give a talk. For those who haven't heard, Electronic Imaging 2021 will be held online. The Electronic Imaging Symposium and conference committees are working now as we speak to construct a program that offers the same great papers from academia and industry with many opportunities to connect, communicate, and network as you would in person. Focusing on ways for people to interact is it's high priority as we plan Electronic Imaging 2021. Electronic imaging can be a bit overwhelming at times, but it's a great place to learn about the ways the fundamental science and technology explored in the academic setting can be incorporated into products and improve our lives and world. For students, it offers registration grants, a student young professional research showcase, a demonstration session, which is a bit like show and tell, conference-based paper awards, and the ability to take courses for free. We encourage you, therefore, to explore what electronic imaging has to offer and to submit relevant research to it. Now, as part of our efforts to provide more value to students, we have been launching this seminar series to highlight best paper research, allow people to learn about areas in imaging outside their subfields, and provide a space to talk more in depth about a technology area. Our goal is to make the program interactive, so after today's talk, we will open the floor to discussion and not just question answers. We would therefore like everyone to feel free to engage and be part of the conversation. To facilitate this, I would like to ask you to please take a minute to rename yourselves on Zoom, if possible, to your first and last name plus your affiliation. This will help us to get to know each other better. We would also like you to turn your camera on if possible. If not now, then when we move to questions and discussions, so we feel that we are working all together. And now, of course, it gives me a great pleasure to introduce Alexandre Fenneteau, a PhD student of Siemens Healthcare France, working in the I3M Laboratory on applying deep learning methods to medical images. Alexandre will discuss a novel multiple sclerosis lesion segmentation method for magnetic resonance images based on convolutional neural networks known as CNNs. He will also look at the pros and cons of using self-supervision for this segmentation task. To you, Alexandre.
Thank you, Sophie. Hop. Then yes, hop. That's everything. Great. It's okay?
Yeah, great. Thank you.
Thank you. So I will talk about the work that we have performed on learning a CNN on multiple sclerosis lesion segmentation with self-supervision. Multiple sclerosis is an autoimmune disease which affects the central nervous system, which means the brain and the spine. It is a disabling disease and it provokes lesions. Its prevalence rate is near 1 per 1,000, but it depends on the regions, and it affects more women than men. The persons are diagnosed around 30 years old in average, which made this disease quite a young disease, affecting young people and disable progressively them. The diagnosis and the following up of the disease is mainly performed with the help of MR imaging. And in those images, we can see the dissemination in space and time. So one illustration of dissemination in space is the red ear lesions that are different positions in the brain. And then in green ear, you can imagine that it is a scan 6 months after the first scan ear, and it appears a new lesion, so it is the dissemination in time and space with the red lesions. The radiologist measure and classify those lesions to orient the patient and its treatment for the future. We wanted to segment those lesions to help radiologists, and to do so, we use convolutional neural networks, CNNs, which are a kind of neural networks in which a neuron is a learnable convolution kernel. The convolution is a mathematical approach that is illustrated in the figure here. Convolutions are used because they are close to the visual cortex analysis, and they are able to create successive feature maps along throughout the neural networks. And at the end, we have the final results, the final task made. So here we can see you input brain and there are some feature maps, and then you have your task, and here it's multiple sclerosis lesion segmentation. The CNNs are a revolution in computer vision. They are increasingly used since 2012, and they are strongly data driven. They are trained with a lot of examples, and they are able to build their own data spaces and data representation. They are used in medical imaging as the great potential to leverage a great amount of data and multidimensional data. They can improve the reproducibility of visual measure, and they can be applied in a lot of different applications, from the acquisition of MR imaging to the analysis that we do here. But there is a problem on using them because of the data availability. As you know, medical data are sensitive data, which are not quite easy to have and to use. Most of the time, we need expert annotation to train our neural network. And in our case, it's radiologists. And it represents most of the time a very long time to annotate examples. There is also the problem of acquisition standardization in those kind of data. To overcome the problem of data availability, of lack of data, most of the time, or a famous approach is to use transfer learning, which consists of use a pre-trained neural network to fine-tune it on a specific task. For example, here you can see an example of transfer learning. You can imagine that you have a neural network able to segment dogs on natural images, and this neural network is trained on millions of images, and it's performed its task very good. So you can reuse this neural network and retrain it for your task of interest, here for multiple sclerosis lesion segmentation. And you hope that the neural network have learned something in common with the first tasks that share something with your task of interest. And in fact, most of the time we can observe that by doing so, we decrease the needed number of learning data for the task of interest, but you have the drawback to constrain the neural network architecture. The question is how to benefit from transfer learning without having a constrained architecture. To overcome this problem, we can use self-supervision, which consists of pre-training a neural network in an unsupervised fashion as a pretext task. Unsupervised means that you does not require any supplementary annotations, and that you are able to find your own example, your own ground truth by yourself in this sentence. So you pre-train your neural network in a task designed in a design task, and then you fine-tune this neural network on supervision on your task of interest. A good example for this technique is the article from the et al. In 2015, in which they pre-train their neural network on predicting the relative position of patches extracting from the same image. And after that, they retrained their neural network for classification. They find that they improved their classification result by doing so. And the idea behind is, for example, when you learn to recognize the relative position of the nose of the cat and the ear of the cat, you are not so far to know what is a cat, and that's the reason they propose. In our work, we wanted to adapt the self-supervision on medical imaging. Here is our method. So firstly, we extracted patches from multi-sequences MR images, because most of the time MR exams consist of multiple sequences which show different aspects of the anatomy and on tissues of the brain here. And then you train a first neural network on a pretest task that we designed to be the prediction of position of the patch position in the whole brain. So it is a regression task, and it consists of predicting the XYZ coordinate of the patch in the brain. The important thing here in this second step is that you can perform this task with whatever image you have. So you are not constrained on one disease or one task, and you do not need annotation. So for example, in an hospital, if you can access to a lot of data, you can use every data you have here. Then in 3, you can transfer the weights of this pre-trained neural network on the segmentation neural network, and then train this network on the task of interest, and in our case, it's on multiple sclerosis lesion segmentation. We used 6 different data sets. 4 were multiple sclerosis segmentation data sets. Most of them comes from challenges, and 2 other data sets from other disease. From the BRATS 2017 is a brain tumor segmentation challenge data set, and the OASIS 3 is a data set on Alzheimer's disease prospects. By gathering all those data sets, we have a problem of data standardization, since images have different sizes, different intensities, and there are a problem of missing sequences also. To deal with this problem, we use a preprocessing pipeline and some other tricks for missing sequences. We kept only one dataset as a testing dataset, which is the MICAI 2016, and the other sets were used for training. For the pretext task, we trained with every training dataset that we had, so multiple sclerosis and other sets. And for the task of interest, for segmentation, we use our multiple sclerosis segmentation datasets. To evaluate our experiments, we firstly design a reference experiment, which consists simply to train from ground zero our neural network for segmentation. Then the OCF version, so the OCF experiment consists of reusing the previous trained neural network and retrained on all layers for the segmentation. Then we did the same with the 1CF version, but with the first convolutional layer frozen, which means it is not retrained during the training of the other layers. The same for 2CF, but for the two first convolutional layers frozen, and so on until the 6 convolutional neural layers frozen. The idea behind doing all those experiments is to respond to the question, are the features learned by the first pretest task enough or need to be adapted for the task of interest? To evaluate our performances and also for training our neural network, we use the Daisco, which is a similarity measure, and which also is the harmonic mean of sensitivity of specificity, which in fact is we can represent it as a compromise between detection of a maximum number of voxels, but correct ones. It is a quite famous similarity measure for segmentation. Here is a box plot of our result presented. We can firstly observe that we obtain quite good overall results, since good Daiscos for the tasks for the multiple sclerosis lesions segmentation are superior to 0.6, so we have good overall results. But we observe that with self-supervision, we obtain very slight improvements, and quite only with the OCF version here and the 1CF versions here, which are in fact the experiments without any frozen layers for the OCF version, and with only one layer frozen for the 1CF version. We see so that freezing in our case decrease the performances and mostly the sensitivity. Here it's a visualization of segmentation. So the segmentation are in color. Here it's one of the sequence in which we can see lesions here in hyper intensity. Here is the ground truth that we used, and in white is the segmentation. Here is the ref experiments with its corresponding segmentation. Here's the OCF version, and so on until the 6CF experiment. In this figure, we can see that more the layer are more we froze layers. So, for example, in the 6CF version, it's the version with the most layer frozen. We observe that the neural network tends to segment a region around the ventricles. Ventricles are the X black things in the middle of the brain. And we interpreted it as underfitting or over-generalization, if you prefer, because we know that most of the time lesions in multiple sclerosis are around the ventricles. And with the version with a lot of layer frozen, the neural network have learned to quite automatically segment those areas. So it's overgeneralized. As a conclusion, we have applied here a novel technique for applying self-supervision on medical imaging. We think that this technique has a potential in medical imaging, and in our case, we have only small improvements by using it. But we think that by investigate better pretest tasks, we can have a far better improvements. And we believe also that other tasks should be maybe more appropriate, since we believe that multiple sclerosis lesion segmentation is quite a simple task, because it consists of most of the time it's a threshold of hyper or hypo intensities, and this is not very difficult for a neural network, and maybe we had too much training data to assess the real performance of using self-supervision. I thank you for your attention, and I'm here for the Q&A after. Thank you.
Okay, thank you very much, Alexandre. I think if you could stop sharing your screen now, and I would invite everyone to possibly put their cameras on if they wish to participate. As I asked earlier, of course, if you don't feel comfortable, you may remain with your camera off. Let me see everyone here. So I would like to ask if everyone has a question. I have several ones, but I would like to ask people first. So you can raise your hand, or you can just throw your question to Alexandre. Nobody would like to start? Okay.
Yes, I have a question, if I may.
Okay, Sander.
Hi.
Welcome.
Thank you. Hi, Alexandre. Nice presentation. Nice work as well. I always respect it when people use artificial intelligence to benefit the medical world as well. So what I was curious about is the main problem that you're trying to solve here is one of too little training data. So I was curious to see if you've also investigated things like one-shot learning or few-shot learning, these kinds of techniques. No,
I didn't assess this.
Okay, because I was curious how they would compare with transfer learning, but okay.
So yeah. Sander, would you, it's interesting, would you like to discuss a little bit what is one-shot learning, very briefly, in comparison to what we heard? Yeah.
So in deep learning, there are many ways in which you try to deal with having fewer data points available than you would ideally want to have to train a good neural network. In this case, that is done by transfer learning, as Alexandre just explained, training on data that is somehow related, and also self-supervision, which you used, where you train on the same data with some other task. And then what I was asking about few-shot learning, which is more about if you only have a few data points, trying to keep those data points that you learn from in some way in memory, so that you can compare with those points more directly instead of trying to completely learn them.
Compare from scratch.
Yeah. So basically, it's like if you're teaching a doctor to try to find these lesions, of course, you can show him hundreds of thousands of images until he understands what these lesions look like. But you can also give him 5 examples of lesions while he is investigating the image, so he can just look at these other 5 images and see if they compare well to this one image that you have before you.
Right.
That would be.
Thank you so much, Sander. Very interesting. Thank you. Anyone wants to chip in or have any questions? So I have a question which relates to the way I want to look currently at CNNs, which has to do with the acquisition standardization that you discussed, Alexandre. We know that, and possibly Sander or other people who work with CNNs could chip in the answer. So I am an image quality person, meaning that I'm looking at the output quality of systems and how this quality interacts with the human visual system. Now here in neural networks, obviously we do not have an observer we have a network architecture, and different network architectures are not standardized, and therefore we can't look at networks in the same fashion that we look at observers in terms of image quality. So now so we have outputs from different scanners, say, or different cameras. In your case, Alexandre, from different scanners. And how I wanted to know how varied are these data, and you have to pre-process them to standardize them, and what do you gain and what do you lose from this making them standard in a way. It's not making them uniform somehow, although the starting qualities are different.
Yeah, there is a problem of, there is three main problems in the pre-processing of data in general. Is that firstly, you have a lot of image from one patient, so you have to register the images inside one patient for one patient, each other, but also most of the time register images from other patients, each others. So it's the first thing. There is also the the image intensities problems, because when you have different acquisition and different scanners, or other sequences that are not the same, exactly the same, you have each intensities on an image is not comparable each other. So here we performed what we call histogram matching.
Right.
So
yeah,
we
you did
tried
discuss it. Yeah.
to make the intensities more comparable each others. And then for the, there is also the problem of data oh, I lost it. Sorry, I have
Don't
those.
worry.
Okay. I will find. There is a pre-processing. This thing. Up there is the. Oh, there is also, when you acquire in a scanner with MRI, you have some bias. You have a big magnetic field, and this magnetic field is not always homogeneous, and you have to correct those things. And we have the chance in medical imaging that there is a lot of algorithm available for doing those kind of things, so you can apply those algorithms, and in fact they work. But yeah, I think there is something in each scanner image will be different, and you will perceive them differently. So yeah, this is an open problem. Even if some preprocessing can help, I think you can distinguish the difference between image acquired in one center and the other.
Right. So there is work for me. It means because I'm really interested in that. I don't know if Sander has something to add on that, just because you are working also with neural networks, what the input quality to the networks. In some ways, in my mind, if you have, for example, a good scanner with a very good intensity, but a bad scanner with less bit depth or more noise, and you try to make them comparable, in a way you lose quality from the one to match a little bit from the other. So there is always a juggling, isn't it? And I wondered what if there are other ways rather than pre-processing and make them homogeneous somehow, the input images, but it's an open question.
And there is also hyper resolution. There are people who are working on hyper resolution. So for example, you acquire on 3D MRI, which are good MRI for the moment.
Very high, yeah.
You want to convert those images to better quality images, as for example 70 images, and some people are working on those kind of things with the help of GANs, and yeah, it's an open field, but
Great.
they work by doing this.
Okay, thank you. There is a hand up on Hong Hongo.
Yes,
Sorry.
Hongo, yeah, you're absolutely right. Yeah,
right.
I do apologize not turning my camera on.
That's fine.
Firstly, Alexandra, very well presentation. Thank you. I really enjoyed it. My question is actually overlap with Sander's question earlier, is regarding, because you are using self-supervision, which is seem to be a very interesting idea for medical image application areas. So my question is very much like how many images you need to be labeled before you can actually having a very reliable kind of a result, either is a classification or segmentation. Because I don't know whether, but I think Sander mentioned about just one. I'm not going that extreme, but I would be interested in saying how many need to be labeled and how many not labeled. So what is the proportion of this could have an impact on this final result? What would be your experience, Alexandra? Sorry, that's my question. Sorry to be sounds a little bit too long. I'm sorry. Yeah.
No problems.
Yeah.
I think for the case of multiple sclerosis lesion segmentation, it is a quite easy task, and we assess after this work, we assess to lower the training data, and in fact, even with quite of 20 exams, we still had good performances. So we can lower a lot the training data set, so the annotation. We can lower a lot the need of annotations. But I think it's task related, because multiple sclerosis segmentation is quite simple. Some tasks, for example, if you imagine classification task of a lot of disease, it should be far more, I believe.
Thank you very much, Alexandra. And I think just for some background, we also work on the medical image, but the images we are dealing with also is a quite large number, and we have some kind of a bottleneck is having enough domain experts to actually labeling it. I think this self-supervision is quite attractive and interesting idea. Yeah, thank you. Yeah.
Thank you.
Thank you, Hongbo. Thank you very much for chipping in.
Thank you.
I don't see any more raised hands, if I'm not mistaken. So I will ask one more question. You talked about precision, the Daisco being the classical precision metric for segmentation, and you said in particular for lesions is 60 or 70%, around 60% is a good score, and anything beyond this is getting better and better, and you have reached around 80%. Isn't it? So, but what this 80% means? Can we rely on a number like that and say, okay, we can use the system now because 80% is good enough? Or what is good enough somehow in order to say that it's autonomous from now on, and we can rely on it as a doctor would?
I think the Daisco is not meant to evaluate are we comparable to radiologists. I think I have saw in some data set that radiologists agreed each other in terms of Daisco at about I think it's 80% or
right.
Yeah, but it's
so we are getting comparable in essence.
Yeah, but it is at the voxel level that it's calculated. There is a most interesting metrics to evaluate if we are closer or not to the radiology score, and it is a metric that it takes a lot of metrics in account, and it is performed by the ISB 2015 challenge. They have performed something, and they display in the article that if you have their metrics above superior to 90%, to 90, it is comparable to radiologists.
Radiologists, okay. And this, I guess, what is comparable to radiologists will depend on the part of the body or the brain that we are looking at, because I guess some parts are easier to segment or recognize than others. So the 60% or 80% is relative to the lesions that we are discussing in your work, not a general thing, isn't it?
Yeah, in general, they account for whole lesions, but most of the time we can see that small lesions are more difficult to segment than bigger ones. Yeah.
And I guess it's the same thing for radiologists, not only for the, Yeah,
it's based on radiologists, when they perform those kind of tasks, they agree each other at a certain point. And even sometimes, if a radiologist segments something at one time and at the other time, it does not segment exactly the same thing. So there is a lot of variability.
Yeah, that they would be experience and other factors. Also, the quality of what they are seeing, I guess. Yeah. And just continuing in the same idea. Do we think that artificial intelligence or neural networks can routinely be used in hospital for medical image diagnosis? Is it going to be, everybody says it's going to be the tool for diagnosis. Do you agree with that? How soon do you see this becoming a rule? A little bit of an insight, and if everybody else wants to chip in on that, because I think it's a question bigger than the work on the brain or on multiple sclerosis. Is a more general thing about imaging, intelligent imaging as a diagnostic tool.
Yeah, I think that it is more and more used. I work also with an hospital, and they begin to acquire some tools based on deep learning, but I think we have to use those tools because you can improve your you can improve your variability. You can lower the variability between predictions and so on. But it remains the tools, because I don't believe that it will replace the radiologist, since it's a good tool for simple cases and also for limit cases. But in those cases, I prefer the radiologist to assess by himself the data and also assess the prediction of those kind of tools.
Okay,
and,
so yeah.
Yeah.
So you see the radiologist using the tool as an additional aid to his prediction, to confirm his prediction or change his prediction or influence his prediction. I don't know if other people are working in medical imaging or Hombo, what he has to say on that.
Actually, that is an interesting point. And unfortunately, for your information, we are working on much worse situation. We are dealing with ultrasound images.
Right, which are much noisier.
Well, it's quite more challenging to actually segment accurately because of the noises and in the background is huge. And so it's quite a challenging situation. But anyway, we are also start working on it. And I totally agree with you, Sophie, that a lot of the points you made earlier is very interesting. And we are also trying to sort of firstly go for almost like a semi-automatic solution where the doctors, radiologists, can make some little bit of adjustment. Because even the so-called the ground truth sometimes may not be that solid, if you know what I mean. Particularly depends on, well, this depends on the image modality, because sometimes even the radiologists, when they provide your reference, they are not solid references as well. So
right, yeah.
Because if you refer to the different radiologists, they give you different ones.
For sure. Sander, you wanted to, I think you raised your hand, or am I wrong? You wanted to chip in on that?
Yeah, I wanted to chip in on that. Also on the disagreement between several radiologists. I was curious, if you're trying to train a network and you know that your radiologists disagree on the ground truth, how do you deal with that?
That's a very interesting question, and there are different ways. And some people, for example, using an approach of having a majority rule, okay, and but that's not always working because it very much depends on the experience of the radiologist, okay. And so maybe eventually, you know, we have to rely on some kind of a, you know, unsupervised result from the machine. And there is a big argument regarding whether the machine one should be used as a benchmark. You know, and I think in a separate work we had many years ago with a department in London in the Imperial College, and they are actually using a kind of they try to use a machine measure as a benchmark, because machine always give you this deterministic result rather than non-deterministic. And anyway, so I can't answer your question with a very clear answer, I'm afraid. Yeah.
Well, maybe there isn't one, and that's the whole interest about it, isn't it? I mean, there is no clear cut about artificial intelligence and whether it will replace or how better or how worse it is from humans. We seem to accept, I believe, human error more than we accept machine error for the moment, but just because we are used to it and we accept the human variability, isn't it?
In fact, if I'm add on that, Sophie, if I'm allowed to, and I think in the Imperial College, there is in London hospital, they actually conducted a test on the so-called inter-observer variations.
Variability,
the range is very, very wide. And then in one of the tests we did, the machine was at least within that range, not beyond that range.
Right. Okay. Interesting. Thank you very much.
Okay, thanks.
And Alexandre, how did you deal with that?
For this study, we use quite the consensus, but also when we didn't have consensus, we train with. For example, for one data set, we had 4 different ground truths delivered by different radiologists. And to train our neural network, we randomly, during the training, chose one or the other segmentation ground truths. And by doing so, we hoped that we had some kind of consensus by training sequentially with all ground truths. Yeah.
I suppose you could also refine that afterwards somehow when you assume that your network is starting to do better than the annotators, that you know which annotators
to use, yeah.
Okay, nice.
We thought also to predict the response of each rater differently. So we trained the neural network to train the response of the first rater, of the second rater, and the third at the same time. But in fact, we tested it with 2 raters, and we saw that it was the same quite the same segmentation performed by the two outputs of the neural networks. So maybe it had found its own consensus by doing so.
Cool.
Right, and now are you continue working on the same topic in your PhD research, or you have changed direction, Alexandre?
We worked a lot on the multiple sclerosis lesion segmentation, but it is a field that is there is a lot of things on the segmentation, but for the moment, we are thinking to apply some other tricks on machine learning on other technique on MR imaging as the diffusion imaging for the moment. So we are not still on the multiple sclerosis.
All right. Do we have any more questions or comments from the audience? Well, if we don't, I would like to thank very much again Alexandre for his presentation. Great presentation and also great paper, and congratulations again for getting an award at Electronic Imaging. And I would like to thank all who contributed to the discussion and all of you who came along. Before we close for today, I would like to remind you that we have more seminars coming. The next one is scheduled for August 12th, the same time, on natural scene detection for self-driving vehicles. So I hope to see as many of you there. Thanks again. I'm going to stop the party now, unless everyone has a last word. Have a good day, afternoon or evening, wherever you are. And I'll see you next time. Bye-bye, everyone. And thanks again.
Thank you, Alexander. Thank you, Sophie.